Now I'm going to start talking about RSA. So the RSA signature was the first public key signature, and here I'm going to give you a brief tutorial on it. I mean, I'm sure everybody knows it in the audience, but let me sort of remind you. In RSA, N is the product of two primes, P and Q. The public key is N and E, and where E is a number which is relatively prime to phi of N. What is phi of N? Phi of N is the size of the multiplicity, the cardinality of the multiplicative group of elements modulo N, which is basically P minus 1 times Q minus 1. So to find such E, it's usually not that difficult, and then you sort of invert the modulo phi of N. If you know the factorization of N, this operation is easy to do because you know phi of N, but we believe that without the factorization of N, we don't know how to do this. It's a conjecture. There is no known equivalence between the two. No, sorry, actually, I stand corrected. Computing D is equivalent to factoring because that gives you a multiple of phi of N, and that allows you to factor. What we don't know the equivalence of is the RSA operation, which is to compute D roots modulo N. This should say here, oops, this should say here modulo N. If given a number in Zn, to compute a D root modulo N is believed to be hard. And we know how to do it if we have the factorization, but we believe that without the factorization, that would be not possible. So once to sign a message M, you take, you hash it, and you compute M to the D mod N, and the verifier will verify by inverting the D root, the E root, and raising it to the E, and checking that the signature to the E is back equal to the message. This is the standard hash and sign RSA signature. We'll talk about different kind of RSA-based signatures later in the lecture. It's secure in the random oracle model, but we're going to try to figure out how to take the secret key and not have it sit in a single server and distribute it among parties so that compromise becomes difficult. So let's start with the very simple case in which we're going to share it among N parties, and all N parties need to cooperate to sign. And let's assume for a minute there's a dealer. Here, the dealer is unfortunately almost necessary. We'll talk about how to get rid of the dealer later in the lecture. But so what does the dealer do? The dealer generates the whole key pair for RSA. So it generates N, E, and D. And then, and here I'm denoting with capital N the RSA modulus, and with little n, sorry for the confusion, the number of parties. Then it takes the secret D and shares it among the N parties additively. What does it mean? What do I mean by that? It chooses random shares in modulo phi of N, which the dealer knows because the dealer knows the factorization. And it chooses them at random under the condition that their sum modulo phi of N is equal to D. Again, the dealer can do all of this because the dealer knows the factorization. At this point, to sign is actually not that difficult because notice that to learn D, you need to compromise all the servers. Do they play the players signs? They sign using the homomorphic property of exponentiation. Each player reveals a partial signature, which is M to the DI, where DI is his local shares. And then obviously, that the real signature is the product of all N signatures modulo N, because remember that because phi of N is the cardinality of the multiplicative group modulo N, the exponents work modulo phi of N. So this should be pretty simple. but the proof of security is already using a very subtle issue. And the issue here is that the parties see random numbers chosen in z to the phi of n. And remember, phi of n is something that not only the parties don't know, but they're not supposed to know. If the parties learn phi of n, they will learn the factorization of n. And what happens here is that the parties are seeing a distribution of numbers which is in 0 phi of n. And the question is, do seeing numbers distributed uniformly from between 0 and phi of n, does that give you any information about phi of n? So, okay, let's prove how this works. It's basically the same interpolation in the exponent argument as is in the case of Deskrivlovsky. What the adversary is what the simulator is gonna do is gonna give random DIs to the adversary, and all that thought there about what I mean by random. And now, if the simulator has the real signature, given the real signature, it can compute the partial signature of the honest players by taking this equation right here, right? And he knows the partial signatures of the bad players because he is giving them DI. He knows the signature S, so he can just go and choose the partial signature of the honest player, so that random condition that they multiply to S. So the question is, where are this DI chosen? From where? The simulator does not know phi of n, so it can't match the distribution that the dealer gave to the real dealer gave to the parties. So the reality is that the simulator chooses them in Zn. And the reason is that n is a very good approximation of phi of n. In fact, the uniform distribution between 0 and phi of n and the uniform distribution between 0 and n are indistinguishable. That is true when P and Q are somewhat of the same size, which is the case when you choose RSA modulus. So, and so this is the subtle issue that comes up when you do additive n out of n RSA signatures. The subtle issue that you don't know phi of n will continue to haunt us and give us trouble throughout the entire set of lectures that I'm going to do about RSA. So let's try to move to threshold. So what if we want to do Shamir over a ring? So the dealer can still share the, remember, why do I want to do this over a ring? Because now we're working modulo phi of n. Phi of n is not a prime, so we're not guaranteed that you can do inversions, first of all. But if we don't know phi of n, we cannot do the inversions. The only way we can invert modulo phi of n, multiplicative inversion, is if we know phi of n. So, okay, so let's see what can we do then. So we choose a random polynomial, f of x, such that f of 0 is our secret, which in our case is the exponent d. So then the dealer, who knows phi of n, sends the shared di to the player. And now the problem is that the set, if you have a set of t+1 players, polynomial interpolation doesn't work. And it doesn't work because the Lagrangians are fractions. Remember last time we said to do polynomial interpolation, you need a field because you need to be able to compute those inverses. And to compute the inverses, in this case, you need to know phi of n. Phi of n is secret. So, and if the participant knew phi of n, they would know the factorization, and so the secret key would be. So what can we do? Remember that the polynomial interpolation formula says the d is equal to the linear combination of the di with some Lagrangian coefficients. And remember that the Lagrangians at this form right here, right? And let's assume that this number right here is invertible modulo phi of n, which means that this number right here does not have factors in common with phi of n. So if you assume that I and j are small, because those are numbers between 1 and n, your number of participants, you want actually phi of n not to have small factors, except for 2. So you're going to have somehow the, you get rid of the 2 by multiplying by 2, and then you have all this stuff right here that will be, you can assume that this stuff right here is invertible modulo phi of n. What the players, however, can do is remove this this denominator from the computation of the Lagrangians by multiplying d by the factorial of n, because the factorial of n has all the numbers that appear and more, but it definitely has all the numbers that appear in this denominator. So if a player reveals, instead of revealing di, a players reveal n factorial di, the interpolation formula will work because all the denominators are cleared, but what you end up computing is not d, but n factorial times d. Is that clear? Any question at this point? So now the question is, what are we going to do with n factorial times d? So let's do our first attempt to build t out of n RSA signature. And I say first attempt because there's going to be an issue with this one. So, okay. So now we're going to do this Shamir secret sharing of d that I just showed you. So the dealer generates the RSA key, shares the secret key d among the parties with this Shamir secret sharing over phi of n. So, and let d1, d2, dn be the shares that the dealer gives to each party. Then the signers reveal si equal m to the di mod n, right? And now remember, we're going to take this di and raise it to the n factorial so that the n factorial multiplies the di, right? So instead of raising it to, so we're going to take s, we're going to compute s to the n factorial. How? By taking the si and raising them to n factorial times the Lagrangian, right? N factorial times the Lagrangian now is an integer, and so we can do this computation right here, and this will give us m to the d times n factorial, okay? So we didn't get the signature, we get the signature raised to the n factorial. But we want the signature. How do we get the signature out? Let's assume that the GCD of e and n factorial is equal to 1. And you can do this because you can choose e to be bigger than n, you can choose e to be a prime, and then this works. And then you use the extended Euclidean algorithm to compute a and b such that a times c plus b times n factorial is equal to 1. And then this is a very famous, it's referred universally as Shamir's trick, that allows you, given s to something which is relatively prime to the public RSA parameter, to compute s. And how does that work? So what is s? S is m to the d, but I can multiply this d by 1. And 1 is a times c plus b times n factorial by the GCD property. And now look at what happens when you split this sum as a product. The D and the E cancel out, and so you're left with m to the A. And what about the other one? The other one is m to the D times B times n factorial, right? But m to the B times n factorial is the signature to the n factorial, which I just received from the players. So I am going to, sorry, this should stay here, s to the n factorial. But I have this component right here, and I raise it to the B, and I have this component right here, and I raise it to the A, and I have my signature S. Okay? And this was, there were other, this was a very interesting story about this paper by Victor Shuk, that somehow this very simple observation had escaped lots of people who had worked on threshold RSA, and up until 2000, people were using different algebraic structures to get to somehow get rid of this problem with the Lagrangians. And in reality, with these assumptions about the set of participants and the prime, you do get a pretty easy solution on how to compute the signature. Okay, so what did I say first attempt? Because, so remember here, the player broadcast m to the DI, and then we get rid of the denominators by taking this partial signature, and instead of raising them to the Lagrangians, by raising them to the Lagrangian time a factorial number. Turns out this is not enough. Let's try our typical simulation with our by now standard 2 out of 5 network. So the adversary controlled 2 players, and now we have a simulator. The simulator gets N and E and starts a network where the simulator plays the 3 good players and the adversary plays the 2 bad players. Remember, how does the simulator simulates the sharing of D? It's just going to give random integers between 0 and n to the to the adversary. Okay, then the adversary says, please give me the signature for a message M. The simulator goes and asks its oracle, and the oracle gives it m to the D. So now the simulator should come up with S1, S2, and S3, right? So, well, the simulator knows m to the DI for the bad guys because it knows DI. The simulator knows m to the D. So it knows 3 points in the exponent of this polynomial of degree 3. So when we were working modulo a prime, we were going to just do interpolation in the exponent to get the remaining partial signatures of the simulated honest players. But here we cannot do it because, again, we run into this issue of Lagrangians, right? And we can interpolate, once again, the Sj raised to the factorial, right? We could do that. But now we don't have a matching EI that would allow us to do Shamir's trick here. We do interpolate this j to the n factorial, but that doesn't give me Sj, which is what the protocol does. Remember, the protocol reveals the regular partial signatures and then gets rid of the fractions when you interpolate. But here, we're not able to get those regular partial signatures. Any questions? We have another fraction that comes in. So, yeah.
We do have a question regarding the n factorial in general. What if like n is large, say like n is 100? How do you work with n factorial?
Very good question. Hold it and I'll get to it in a minute. Okay. Yeah, it is an issue when n is large. This is a very big issue, particularly because when you raise to the n factorial, you can't take n factorial mod phi of n because you don't know phi of n. So you have to raise to the n factorial as an integer. So that is a very good question, and it's coming up in a couple of slides. But right now, I hope you all understand why this scheme where you're revealing just the basic partial signature gets stuck in the simulation. So here is what we're going to do. What we're going to do is that the players do not reveal m to the di, but they reveal m to the di to the n factorial. Why? Because I just showed you that that's what I can simulate. Okay, so now then I do my interpolation. Again, I have to multiply to the n factorial to get rid of the Lagrangians. So what I end up with is the signature raised not to the n factorial, but to the n factorial square, which makes things even more complicated with respect to the questions that we just had. But we're going to do the GCD trick again, assuming that z is still, obviously, if n factorial is relatively prime to e, then z is also relatively prime to e. Okay, so clear what's going on now? Now n factorial comes twice, comes in the exponentiation by the players of their partial signature and in the interpolation. This one right here, we needed to make the interpolation possible, and this one right here, we needed to make the simulation possible. Okay, and now the simulation is going to work. Remember again, where the bad guys have random shares, the simulator on input on message m gets a signature from a centralized oracle, and now the simulator computes the modified partial signatures. Did I miss an n factorial here? I think I missed an n factorial here. It knows this one right here. Oh no, the modified partial signatures, I mean the actual ones with the di, without the n factorial. So those are not the real partial signatures that the protocol defines. Those includes the n factorial. So I gave them a new name, ui. The adversary knows these values. It knows this value because it gets it from the oracle. It knows these values because it knows the di. And now it can interpolate in the exponent by multiplying by n factorial. And that gives him exactly m to the di to the n factorial, which is si. So now by defining the partial signatures as m to the di to the n factorial, we're able to get the simulation to work. Any questions? And then, of course, there's a final part in the simulation, which I'm not showing, that at this point, the adversary is seeing the same view that it would see in a real execution, and therefore it will forge with the same probability as it will forge in the real execution. And if it forges, then the centralized simulator forges in the centralized. The simulator forges in the centralized scheme, which we assume to be impossible. So and this is how the Shoup threshold RSA works. And here is the question, here is where we're going to address the question that just came up before. In the previous solution, the value n is a parameter to the scheme. This is already, it requires parties to do computation which is linear in n. And why? Because you have to exponentiate to n factorial. And again, you have to exponentiate to n factorial, where n factorial is an integer. You're not going to be able to reduce n factorial to the size of the group n, because you don't know phi of n. So one issue is, what if n is really large? Yes. The other issue is that you are putting this very strict coordination in the network that players are exactly identified with the integers between 1 and n, right? There's nothing in anything I've said so far. I've used the identifiers I to be between 1 and n just for convenience. Everything I've said so far works even if the identifiers are your MAC address, the hash of your email address. You can use any unique identifier. As long as players have unique identifiers, you can use the unique identifier as the evaluation point for Shamir secret sharing. It doesn't have to be I. I assumes the specific coordination in the naming space, which may not be possible if you assume like what I call here ad hoc groups, where people come in, come out, they come in with this identifier, which is like their network identifier, and so on. So if your identifier is a k-bit string, then now we're going to have computation which is exponential in k, because n factorial becomes 2 to the 2 to the k, right? Because I had to assume all possible identifiers, and that is just not going to work. So where is the factorial coming in? The factorial comes in two places. One is when we interpolate, right? To remove the Lagrangians, the denominators from the Lagrangians. The other n factorial comes in when I reveal my partial signature, and this one is really an artifact of the proof, okay? So let's look at the two of them separately. So the one in the computation of the signature can actually be somehow compressed. You don't really need to use n factorial, right? You know the parties that are participating in the computation of the partial signature. You say, oh, this t+1 parties come in, you add their t+1 identifiers, and so you can replace it with rather than with the n factorial, with the LCM of all the denominators that appear in this in the Lagrangians, in the proper Lagrangians. And here I'm using I minus j, but again, this could be the identifier play I and the identifier play j. Okay, if your identifiers are up to 2 to the k, then this number is going to become much smaller. It's going to become 2 to the k over t rather than 2 to the 2 to the k. So this is actually a very almost trivial observation. The issue is the one in the reduction. The one in the reduction is an artifact of the proof, which means in the real execution of the protocol, I cannot assume that I know what is the set S that's going to come in the reduction of this. You know, it's basically the set of the bet players, right? And that is, again, I would have to know in the course of the execution of my protocol who the bet players are in order to do something like this. And that, I don't know. So I don't know how to remove this n factorial. And let me tell you again pictorially. So remember, the simulator can compute these guys, but so it doesn't know how to compute. To compute this guy, he would have to do this n factorial trick. But to get rid of this denominator, which is a denominator, the ZA, which I'm going to call ZA, which is the product of all the denominators of the adversarial Lagrangians. Now, if I knew, actually, this could be the LCM, not really the product, right? So if I knew ZA, then I could do the same trivial trick that I showed here. If I knew ZA, so instead of raising to the n factorial, sorry, I would raise it to the ZA, and the simulation would go through. But I don't know ZA. So in the simulation, if I don't want to use n factorial to cover all possible ZAs, I would have to compute the ZA root in order to really compute the Lagrangians in the interpolations. So here we're stuck, right? So the only way we were able to prove this was by introducing an extra assumption on the security of RSA. And the assumption is that when you start the game, instead of having this game right here where the simulator sends a message M and you get back a signature, M to the D, the simulator is allowed to also provide the challenger with a exponent of its choice, which then it will get not just M to the D, but it will also get the ZA root of M. So it gets at the E root of M, but also this additional root of M. And what we conjecture is that if E and ZA are relatively prime with each other, this is not going to help you find E roots, okay? So now, if we're having this nice, helpful challenger here, then we have the information that allows us to complete the simulation. So this threshold RSA, where you raise to the factorial, you can remove the factorial in the partial signatures if you assume the stronger version of the RSA problem, which, by the way, in the random oracle model where ZA is actually is equivalent to the regular RSA, or you have to put the factorial in, okay? So we deal with this factorial by adding this extra assumption, and we remove one factorial, and the other factorial we compress it simply with the right multiplier, which is the LCM of the players who are reconstructing the signature from the partial signatures. Any questions so far? Okay. So everything I've told you so far works for honest but curious players, which always output the correct partial signature. Now the question is, how do we detect bad partial signatures? Because even a single partial signature would prevent us from, well, one is actually not bad because you try all possible subsets until you find the signature that verifies. But again, remember this, for T bad signatures, that would give you an n to the T algorithm, which may not be practical. So I'm going to show you two ways of detecting partial signature, bad partial signature. And the first one is based on message authentication code. So at the beginning, the dealer, when the dealer sends a shared DI, the dealer also chooses triplets, AIJ, BIJ, and CIJ, such that A times DI plus BJ, BIJ is equal to CIJ. And this, for those of you, many of you may recognize this as the universal hash function based authentication code. we need to do this over the integers. Even if the dealer knows phi of n, he's going to choose AI and BJ. So he's going to choose AIJ and BIJ on sufficiently large random integers, and then set CJ this way also over the integers, okay? The reason that the dealer is going to do this over the integers is that he's going to send Cij to player I together with his shared DI, and Aij and Bij to player J, okay? Now here you see why we have to do this computation over the integer. If he had done this computation modulo phi of n, if I and j, since he's giving this to every pair of players, if I and j are both corrupt and they collude and they pool their information together, this equation right here, if done modulo phi of n, would give them a multiple of phi of n. Multiple of phi of n is equivalent to factoring. So the dealer has to do this over the integers. Now, when the player I outputs the partial signature, he's also going to output m to the Cj. And it does this so that player J can verify that the partial signature is correct, but verifying the message authentication code in the exponent right here, okay? So the player J accepts this partial signature if this equation right here verifies, which is the message authentication code. This is an information theoretic message authentication code, and it will work in the exponent because it's a linear operation. What I'm not showing you in the slide, you can go look at the paper, is that A, this is still a good message authentication code, even if I do it over the integers. And this depends on how big you choose these parameters. And B, that while this is, if you do this modular prime, this is a one-time message authentication code because it, once you use it once, it's done. You can use it again to authenticate a different message. But here, it allows us to, because what changes is m, it allows us to use it several times for every different m because we're doing it in the exponent. And basically, the algorithm that would help you break the message authentication code, if you use it more than once, you can do it because it's hidden by the modular exponentiation, which is a one-way function in the RSA one-way function. So those are the two technical issues in this solution right here, that the code has to work over the integer and that this equation allows you to do it repeatedly. So this is the first one. The other one, and then I think would be a good place to stop, is to use zero knowledge. Zero knowledge, we do that by the dealer is going to augment the sharing phase by publishing a public commitment to the partial share. So G to the DI will become a commitment to DI that everybody knows. And remember that the partial signature is M to the DI, right? So this is if you do our things where we remove the n factorial, but even with the n factorial, you can put the n factorial in both of them. It doesn't matter. What matters is that what is necessary is that the player has to add a zero knowledge proof that SI and GI have the same decimal log with respect to M and G. This requires, that one technical complication is that it requires restricting everything to a cyclic subgroup of Z and star, which, for example, of sufficiently large order. And for example, if you use safe primes, that could be the subgroup of quadratic residues. Okay, so what are these proof of knowledge, the zero knowledge proofs for groups of prime order where there's some really, so we need them in groups of unknown or unknown composite order, but let me show you first how they work in groups of prime order, and this is very old work by David Chow. One is basically a duplicate of the Schnorr proof. I'm going to send you, remember I have to send you that y is equal g to the x and s is equal m to the x. I'm going to send you g to the r and m to the r. You're going to send me a challenge, and I'm going to open a linear combination of the secret and the random nonce, r plus cx mod q, and you check two Schnorr equations with the same things. Because you're using with the same things, that guarantees to you that the x is the same across. This is a public coin proof. Can be made non-interactive with via Shamir. It also very nice property is that it's a proof for knowledge of x. Another one is a secret key coin in which the verifier chooses A and B at random and sends G to the A, M to the B, because the prover will respond this with C to the X, and the verifier checks that the C to the X is equal to Y to the A, S to the, this should be B right here. And that guarantees that Y and S have the same X as the exponent, because the prover has no information about A and B. This is a private coin, cannot be made non-interactive. It's a 2-round honest verified zero knowledge. You can turn it into 4-round full ZK by standard techniques. How do you do this with unknown order? The first one, instead of choosing R remember, you don't know the order of the group. So you're going to choose R in a pretty large set, maybe slightly bigger than that. And the challenge is going to be in an integer set as big as your security parameter requires, because this is where your soundness level is decided. And then you answer, but where in the Dasku log case, you will know the modulus, and so you would take this equation modulo q. Here, you want to take this equation over the integers. And that's why you need to choose R large enough. And then the verification equation remains the same. So you choose R large enough so that this answer right here statistically hides X. In fact, you can prove that this is a statistically zero knowledge proof. The other one, you don't even need to do that. You choose A and B in Zn simply because you don't know phi of n, but it's enough to choose them in Zn, and the proof proceeds exactly as Chow proof. So, okay, and that's, I guess this is a good place to stop, because now we're going to change topic. And once you detect who's contributing bad shares, you kick them out. You have enough good shares, and you can, if you have enough good shares, then you can reconstruct the signature. So, and I think this is a good place to stop.
There's one question.
Yeah.
When we use threshold RSA, it would likely be nice to have a distributed protocol for generating the public key.
That's the next.
Okay. The question was: are there any practical protocols that also do it in such a way that you have safe primes?
I think is Kamit here? I think she's the right person to answer that question. I know that there are protocols that give you Blum integers. That is not difficult to do. And by the way, for what I just told you, I think Blum integers are sufficient. You don't really need safe primes. It's to have the quadratic residues being a large subgroup. I think it's enough for your integers to be Blum integers. But I'm not sure. I suspect not. But if Kamit is here, she can probably correct me. I don't think you can have the distributed protocols give you safe primes. We'll talk about the distributed protocol after the break, but
with regards to the zero knowledge proof here, can the size of the R in the zero knowledge proof be reduced by doing something akin to the Fiat-Shamir with a Ward's approach for lattice signatures?
No. So the size of R is really your size of R has to compensate, first of all, for CX getting bigger, right? So, and then of course you can choose a smaller C, but that would give you a smaller security parameter, right? So the size of R is really required to be an order of magnitude bigger than CX, so that the noise of this randomness completely overwhelms whatever information you have about X. What you want is that this value right here looks like it's uniformly distributed no matter what X is, right? Because in the simulation, that's what you're gonna do. You're gonna choose D at random and you're gonna work backwards, right? You're gonna choose C at random, you're gonna choose C at random, and you're gonna set A and B according to these equations. Think about the interactive case, right? So then we're random where? Random where you're gonna choose your interval this big, and if you choose the same D in the same interval, if CX is relatively small to this NB, the fact that you're adding CX is not gonna mess up the distribution too much. That's basically what the proof is. So I don't think that using Fiat-Shamir will help you reduce the size of R. And by the way, these are all efficiency concerns because these are all exponentiation that you have to do with this integer, right? You can't like reduce it in any way.
Okay.
Okay, so thank you, Rosario. I also have a question.
Yeah.
Are there applications where they prefer to use RSA signatures and not discrete log-based signatures? Because they're much more complicated to use in threshold.
Right. No, so the only thing that I can think of is certificates, right? And because those are like if you think about all the applications like blockchain application and all of that, you have BLS, you have DSA, those are much shorter. First of all, they're much shorter signatures than RSA, so people use those regardless of the threshold, and then the threshold is also easier, right? So when we did RSA, it was back at the time when we were working on thinking that certification authorities were going to maybe use these things. And no, I don't know of any application that uses specifically RSA signature in threshold fashion, partly because of so actually the protocol itself is not that complicated, except that you need the issue is the key generation, which we're going to talk for a minute. And in fact, the main motivator for the distributed key generation is really not RSA signatures, it's more distributed Payet decryption. But we can talk about that later.
Yeah, I guess it matters for backwards compatibility if you need it. Yeah.
Right. So if you have a system where you're signing with RSA and you don't want to change it and you want to protect your key, you can do this. And again, remember, a one-time dealer, the shares in some circumstances may not be like an issue, right?
Yeah. Okay. Thank you.
So now we're going to talk about, again, how do we generate RSA keys without relying on a dealer? Remember, if our goal is not to have single point of failures, then this RSA key should be generated jointly by the parties rather than having a dealer know the key, even if it's a single point of failure, which is somehow limited in time to just the key generation. Now, if DKG is already sore point when it comes to discrete log, it even so more a problem when it comes to RSA. And the reason is that removing the dealer is not as easy as in the case of discrete log base key. Here, the dealer is not just generating a random value. It generates two random primes, multiplies them together, keeps the factorization secrets, and then he has to generate the values E and D. To replace the dealer, we have to come up with a protocol that does all of the above with the secrets shared among the players. Now, in principle, you could use an MPC protocol, but because we know that MPC can do anything, but this would still be a pretty difficult task to perform efficiently, because if you think about how centralized RSA generation works, you select a random prime, you run the Miller-Rabin primality test until you select a random number, you run the Miller-Rabin primality test until you find the prime, then you do it again, and then you multiply the two primes together. The bottleneck to do this distributively would be really the Miller-Rabin test, and that's because the Miller-Rabin test perform several modular exponentiations, and you would have to do this modular exponentiation in a distributed way. So we're going to see how the biggest contribution here is to move. It's not that you're going to do less modular exponentiations, because then you will get a better primality test, right? But what you're going to do is remove the modular exponentiation from the distributed computation, but move them locally to each player. And that's going to be the biggest advantage on how to do generation in a distributed way. This has been a very active research area in the last, I think that every year in the major conferences, there is a paper getting some improvement on this. As I was saying before the break, the motivator for this hasn't really been threshold RSA signatures, as much as the distributed generation of an RSA modulus for a Payet encryption scheme, which uses also the factorization of n as a secret, because it allows several MPC protocol to run faster if you have a shared Payet key among the players. In fact, I didn't talk about that yesterday. There's even a paper that you can do threshold DSA much easier if instead of having individual Payet key to do that MTA, you actually share them among, you have one with a shared decryption key among the players. So this goal goes back to this seminal work by Dan Bonnet and Matt Franklin on how to generate RSA keys in shared form. And as I said before, the biggest goal there is to avoid using the Miller-Rabin primality test. So let's think about how, let me break down in phases how the Bonnet-Franklin scheme works. The first task is that the parties will generate together a random number, and then we'll do some very simple preliminary sieving to make sure that it's not divided by small primes. And this is just to avoid doing the more expensive steps that come later too often. Then, say that we have two numbers that have passed this preliminary simple sieving step. Then you multiply them. So P and Q, they'll be in shared form, and I'll get into the details more in a minute. But the parties will multiply and get n. And now the test is going to be on n, which is public. that this test is not going to be that n is prime, but that n is bi prime. But bi prime, we mean the product of two primes. Now, if this test succeeds, this is a randomized test. There's false positive cases, but if the test succeeds, then we assume that n is bi prime, and then at that point, the parties compute E and D. Okay? So those are the steps, and now we are going to slowly go one by one. So the sieving and the multiplication are actually not that complicated. So, and I'm going to really hand wave a lot of it, because otherwise we'd have to do an entire hour on the Bonnet-Franklin paper. But the paper is, it's actually really well written, and it's pretty easy once you have this roadmap to sort of understand it. So I would encourage you to read it, because it is, by the way, the basis of all the papers that came later. Every paper that came later is just follows this roadmap and just optimizes each of these individual steps one by one. So let's start with the first steps. So what do the parties do? They generate a random number, and for the moment, let's just assume that we're an n out of n scenario. You can do all of what I'm saying with Shamir, but let's just for simplicity do n out of n. So each party generates random numbers, pi and ri, in pi in a certain bound, which is the bound of the size of the prime numbers that you're interested in, and ri has to be a slightly larger bound, because it's going to act as a mask that will mask P when we reconstruct PR. Okay, so again, we have PI, which is shared additively among the players. So P is the sum of the PIs, R is the sum of the RIs, and if you remember, we have to reconstruct the product. You may want to remember from yesterday that we do have a way to do this through pairwise multiplication and all this thing of changing multiplicative shares into additive shares. Actually, when Bonnet-Franklin did this, they used something different, but then you can do it with the MTA protocol, which is exactly what then later Gilboa did for the two-party case. Okay, then the next step is that you want to sieve, right? So for every small prime that you want to sieve, you reject P if PR is equal to 0 modulo A. Why? Because if PR is equal to 0 modulo A, that means that A must divide PR. And if R is pretty large, then the chances that A divide R is probably not that large, and so there must be that A divides P, right? Again, probabilistically, so that will, you may reject a good P, but most likely you're going to reject a P that is divided by A. And you do this for a bunch of primes up to whatever bound you're interested in. So, so let's assume now that we have passed our test, and now given two such numbers P and Q, remember P is additively shared, Q is additively shared. The party reconstruct the product. Again, this is the multiplication additively shared values. We know how to do it, at least in principle. So, okay, so we have now an N. What we know about this N is that P is the product of P and Q, and then P and Q are not divided by small primes. Now we want to make sure that P and Q are really primes. So here I'm going to show you a very simplified version of this test. It's called the Jacobi test. So if N is the product of two primes, then phi of N should be P minus 1 times Q minus 1 should be the order of Z n star. That is not true if N is not bi prime. That's basically the idea of this test. So what are you going to do? Well, remember that the parties have an additive sharing of phi of N. Why? Because they have additive sharing of P and Q, and they have N is public. So all they have to do is use their local shares on P and Q to get an additive share of phi of N. So for example, if the first player will put N and 1 in its shares, and all the other ones will use P1 and Q1, okay? And now you're gonna repeat many times that you choose a random value G, and you test that G to the phi of N is equal to 1. And if that's the case, then you are going, actually you have to do P plus or minus 1, but basically this tells you that phi of N has to be the order of the group. Okay, this I'm hand-waving, I'm trying to get you the concept across. There's very subtlety there, but this is the basic idea. Now, here is where the things get very interesting. To do this test, the exponentiation has to be computed locally. All a player has to do is take G and raise it to the phi. And this gives you GI. And then you cannot reveal the GI. So you have to do a distributed computation to check that this product is equal to 1. You're revealing the GI will probably give you information that you don't want to reveal. Okay? So notice that the whole advantage of using this biprimality test is that the exponentiation is being pulled out of the distributed computation and is done locally by each player. Okay? There's also an additional GCD test that is required, which basically checks that N and phi of N are relatively prime. And then once you've done all of this thing, you have this probabilistic guarantee that N is the product of two primes. Now you're left with the inversion of our share sequence. And here I'm going to show you not the protocol that is in the Bonnet-Franklin paper. I'm going to show you a different protocol that I wrote together with Dario Catalano and Shaya Levy later on. It's more efficient than the Bonnet-Franklin at the expenses of yielding slightly larger shares of D, which that would give you some sort of inefficiency later when you want to sign with this D because they're bigger. But the protocol itself is much simpler, not just computationally, but also conceptually to explain. So I chose to show you this one. So by the way, so what do we want to do? We have N, we have phi of N, which is shared, and we have E, which is public. E, you can choose, you choose a prime, you choose, and so you're fine. So now, you make sure, so now we want to make sure that we want to compute a sharing of D. This is the dual problem of the one that we saw yesterday for the case of DSA. In DSA, we had a public modulus, and we had to invert a share secret. Here, we have a public value to invert, but modulus a secret value. Okay, so you see the difference between the two. So how are we going to do this? The parties have an additive sharing of phi of N. And so what they're going to do, they're going to choose a random value in a large enough interval, again. And this is in additive shares, again. And then they'll reveal this value right here, phi I plus ERI, calling AI, and set A the sum of the AIs. Now, if you do this, obviously, what are you going to get? The sum of the phi I give you phi of N, and the sum to the RIE gives you RE, right? And here is why you want to choose R large enough, because this is going to be good enough. Everything is over the integers, so if R is large enough, this value hides phi of N statistically, and so we are not revealing any information about phi of N. Another disadvantage of the Bonnet-Franklin protocol was that it was revealing a few bits of phi of N, not many, so it wasn't much of an issue, but here we reveal nothing. So now, if the GCD of A and E is equal to 1, Then there exists B and C such that A times B plus C is equal to 1. Okay, so let's see what that gives us. So 1 is equal to A, B plus C. But what is A? A is phi of n plus RE. So if you plug that in, you get B phi of n plus BR plus C times C, right? You're going to take this BR and put it in here because there is the E in front. Okay, takes this equation modulo phi of n disappear, and you're left with 1 equal BR plus C times C, which means what? The BR plus C is the inverse of E modulo phi of n, which is exactly what we were looking for. And here you see why you're getting a D, which is somehow a bit large because you want this R to be substantially large than phi of n, right? So you're going somehow an order of magnitude, probably the size of n square, to get your statistical secrecy, which makes your shares of D somewhat bigger, right? Because now you can set your shares of DI to be just there should be a C in there, right? BRI plus C, obviously. Well, I think C goes only in the first party, so you're right. So C goes, one party adds C and the other guys put BRI. Any questions? So this is basically the bare bones explanation of how Bonnet-Franklin works. So, by the way, allow me a little detour, which tells you why we did this, even after. So we did this work after Bonnet-Franklin appeared. So there was already a protocol for this. Why didn't we like the protocol that Bonnet-Franklin had? The reason was that we looked at this problem for in the context of thresholdizing other signature schemes based on RSA, which are the signature based on the strong RSA problem. So far, when I talked about the RSA signature, I've been talking about the basic hash and sign, which is proven in the random oracle model. There are actual other signature schemes which do not rely on the random oracle model, and they're provably secure based on the strong RSA assumption. What is the strong RSA assumption? Is the one in which instead of giving you n and an exponent, I give you n and a fixed group element, and you are allowed to choose the exponent for which you're going to get E roots. So the adversary is allowed the choice of the exponent E, and then is able to compute E roots with that exponent. We believe this E roots of this fixed base. We believe this to be a hard problem. And the signature schemes, I'm not going to go into full details of the signature schemes based on this, on the strong RSA, but they both work with this idea, which is that the public key is this n and this fixed base, and the secret key is phi of n. The message m is mapped into an exponent m, and the signature is the m root of G, where m varies with every exponent. And this sort of tells you why you need the strong RSA, because now the message is under the control of the adversary, which means the exponent is under the control of the adversary. And remember, we don't want random oracle, so you can't say, oh, the message is mapped into a random exponent. There are two ways. One is the message m is mapped for a deterministic function that output primes into m, and the other one is a randomized, where from every message m you select a random prime in some way. So, and at this point you can verify by checking that S to the m is equal to G mod m. And these are the two schemes that I know of. One is, the first one uses this deterministic mapping of m to the exponent, and the other one uses a probabilistic generation for this exponent. And to make the schemes into threshold ones, we need exactly the protocol that we showed before. Computing the sharing of the inverse of M, where M is public, but the modulus is secret and distributed. And one reason we didn't like the Bonnet-Franklin inversion protocol is that it leaked those bits of phi of n on. And while it is okay to leak a couple of bits of phi of n once when you're generating n and then you're done, because you can always guess those few bits, it wouldn't be okay to leak bits every time you sign. Then you probably risk leaking too many bits about phi of n and breaking the scheme. So we wanted something that leaked nothing, and that's why we went back to the drawing board and didn't use the Bonnet-Franklin modular inversion protocol. Turns out that the protocol is even simpler at the cost, as I was saying, to give you a slightly larger D compared to the Bonnet-Franklin. Any questions so far?
No questions so far.
So this, I gave you the bare bones version of the Bonnet-Franklin. Let me tell you, I gave it to you in the N out of N case. If instead of using N out of N sharing, additive sharing, you use Shamir, it still works. You require honest majority for those multiplication protocols that I told you about, in which I sort of say, oh, you have the shared values, you gotta multiply them. And it was only proven for the honest by curious setting. So there were several papers. The first follow-up paper was actually this paper by Gilboa that shows how to extend it for the two-party case, which is exactly where this MTA protocol that we discussed yesterday was introduced. There have been many follow-up works, and I'm not going to get into them because they evolved. Again, it would take me the entire 4-hour school to cover them. I don't think Kermit is here today because she would be the perfect person to present this, since she's been very active in this area. There have been many protocols that have been presented following the Bonnet-Franklin approach, but they all follow this basic blueprint that I showed you. And the improvement have been focused on, the first one is getting a better sieving at the beginning so that we can avoid running the biprimality test too often, reducing the communication complexity. For example, the last paper by Kermit and their co-authors uses a distributed version of the MTA protocol where the additively homomorphic encryption is not, there isn't one for each player, but there's a single one which is with a distributed decryption key. But this is sort of like a circular problem, because if you use Payet, then you would need a distributed generation of RSA to have this distributed Payet, right? So they don't do that. They use a lattice-based additively homomorphic encryption scheme and use that to give you the threshold version. And we'll talk a little bit about the threshold and lattices in a minute. And then there is a lot of works that have been adding the security against the malicious adversary just by adding the appropriate zero-knowledge proofs in the various steps. The first paper that did this was a paper by Frankel, Young, I'm not sure, there was somebody else in that paper. The last paper by Kermit and their co-authors uses recent advance in SNARKs, which are important because they have sublinear size proofs. So they reduce the communication a lot, and in some cases also sublinear verification time, which reduces the amount of computation that each party has to do. So again, this is not the only paper. There was another paper last year also, which I really liked which was this, the beautiful title was The Return of Eratosthenes. Again, focus on doing much better sieving to reduce the overall complexity of the scheme. And also they use a different way to enforce security against malicious adversary, which somehow reduces the use of zero knowledge proofs. They do this consistency checks where they reveal things that are going to be wrong if the adversary has been malicious, but at the same time, don't reveal any information about the private values of the players. So lots and lots of interesting optimization, but overall, the paradigm remains the one of the Bonnet-Franklin scheme. The bottom line is that we can now generate distributed RSA moduli for thousands of parties in a matter of minutes. This is why the numbers that were reported by this paper that I have referenced up there. As I was saying before the break, threshold RSA signatures is not really the main motivator of this line of research. The ability to have a threshold version of the Payet encryption is really what's been motivating this this line of work, because that would give you more efficient multi-party computation protocol in general.